Welcome back to this course, Introduction to Cloud. This is a presentation of Coding Boot Camps. This is session 4, Introduction to Docker. What we've learned so far. So we had our overview of cloud computing, the varieties of cloud computing and types of services, including public varieties, private, hybrid, software as a service, infrastructure as a service, and platform as a service. And we discussed DevOps. So the IT landscape is changing. Application development needs to be done faster with more features, more runtime environments, such as mobile. DevOps needs to be used to automate that delivery in order to respond to the demands of the marketplace. And cloud is changing the landscape as well. It's allowing even small firms to have the access to large computing infrastructure. Movement to the cloud. So it's believed maybe around 80% of the movement to the cloud is complete. So, and this includes migrating workloads to the cloud, portability across environments, so the cloud enables that, and avoidance of cloud vendor lock-in, which could be an issue. Once all of your data and all of your infrastructure, your virtual infrastructure is with one cloud vendor, it can be difficult, it can be a task, it's not impossible to migrate away to a different cloud provider. So make sure you have the proper agreements in place, which will at least smooth the process of migrating from one cloud services provider to another. We can see here applications are transforming. So at one time there was the monolith, so the large hardware, very slow to change, big servers, all applications ran a lot of times on premises at the firm. Whereas today there are smaller microservices which are connected quite often over the internet. They are often loosely coupled services, rapidly updated, very reusable, and small services, and also services that can act as backups for one another. So it is almost like the monolith, but just operating in pieces instead of a one monolithic structure. And application monitorization. So there was application code, and there was minor code changes required a full compile, often a retest, any kind of regression testing. Applications became a single point of failure, and applications were difficult to scale up because if all of the computing infrastructure was within the firm actually had to budget all of that physical hardware. So if we break into microservices, each microservice can specialize in its section of the application. And 12 factor apps make the apps more independent, more scalable, more stateless, and highly available by design. So we can see here again continuous integration and delivery. So there is a version control quite often provided by Git or a similar tool. The developer checks all of the code into the version control repository, and then testing can happen. So Jenkins here, we can see Jenkins can actually build the source code that the developer developed. We can see it here, source code comes in and executable code comes out. And even some QA can happen during this time. So obviously, if the code builds, that's a test right there, because quite often builds can fail. And automated tests can run during this time. Automated tests such as JUnit testing. And then the environment, through automation, can actually stage to pre-production environments and eventually to production environments. And all this time, we can see the developer role here in the development section. a QA analyst or quality engineer operating the tools and the automation during the test phase, and then a system admin making sure that the product is stabilized, it's monitored, and it's secure. So this has come up for a long time. There's been a tug of war and often conflicting ends for developers and operations. Again, developers want to continuously improve and fix applications. Product managers, the same thing. They want to increase functionality, add capability. IT operations, they like to stabilize. So they want to, once they have something running and secure, a lot of changes, a lot of updates could disrupt that stability and that security. So organizations must deal with that diverse technology. So bare metal, obviously that's hardware right out of the box, on premises, adding in operating systems and some kind of traditional security. Plus that now there is the ability for virtualization. So having several different computers share the same hardware and make the hardware more efficient, the same disk, the same memory. Cloud, where typically a cloud provider, an off-site data center, is able to manage my computing infrastructure for me. And when I need more, I can simply just request more. When I don't need additional computing resources, those computing resources go away. Windows, again, we have our different operating systems, not only Windows but Linux, and these microservices which allow for specialization of running certain sections of the application or even devices. And when it comes to this, only the microservices that need updating receive the updating. So again, the diverse organizations, again, developers, they need the freedom to create and deploy fast, define packages. IT operations, again, very important to secure, very important to stabilize, to measure, to make sure the customer is getting the value that they are expecting. And here is the myth of bimodal IT. There is the microservices world, usually associated with cloud and new infrastructure. So we're either here or we're in the traditional part, the traditional quadrant, the old infrastructure. So you're almost never in both the traditional and the microservices. You're in one or the other. Enabling the journey again, or the microservices, the agility, and our traditional applications. So this is our journey from the old infrastructure to the cloud and the new infrastructure. So let's look at Docker and containers. Let's look at the overview. So here, a little bit of history. So Solaris, in around 2004, creates Solaris containers, and Zone Technologies are introduced. So containers can be thought of as just the application and the dependencies running on top of a common operating environment. Then in around 2008, Linux containers were introduced. And then Docker is started as an internal project. And then Docker is then released in 2013 as an open source product. Docker continues to introduce the first commercial product, now called Docker Enterprise. And the difference really between the community edition of Docker and the Docker Enterprise is support. So if Docker Enterprise is desired, the users would just pay for support of the Docker tool. So today, there are more than 3,000 open source communities, more than 43,000 contributors to Docker, and there have been more than 12,000 forks of the technology, meaning that different development paths have been created for Docker. And there has really been incredible adoption in just 4 years. So we can see here that the Docker hosts 14,900,000 Docker applications. The growth here in Docker job listings has gone up by 77,000%. Images have grown. and also the number of contributors have grown in just a relative short amount of time. A little bit of a history lesson. So this was the physical server, the physical hardware. There was actually physical hardware that was built. So we can see the physical layer here. The operating system is a special program that's installed that runs on this hardware. It's built to run on this hardware. And then there are applications that run on top of the operating system, and the operating system is in charge of managing the resources for this application, including memory, disk, video, and other resources. But there are limitations of when it comes to managing applications in a physical environment. Number one, you have to have enough physical environments for the demands of your application. So scaling was hard. Slow deployment times, because a lot of times the configurations of the operating systems could drift, could change slightly. Updates could happen at different times. Environments that were thought to be absolutely identical turned out not to be identical. Wasted resources, huge costs in managing all of these physical operating systems, including electricity and backup. Difficult to scale, so it required a large budget to scale. Difficult to migrate, as these systems need to be upgraded. It takes time and effort. And yes, vendor lock-in as well. So quite often it limited the options of the firm to go with physical software and hardware. And a little bit of a lesson here in virtualization. So virtualization, this is a brief description of virtualization. So there is physical hardware and a host operating system and a special program or a special application called a hypervisor. And what a hypervisor is, it's a tool, a software tool that allows you to control guest operating systems. So different guest computers run separately on the hypervisor with their own IP address and their own host IDs and their own instance of the operating system. So they share a common operating system, and they share a common physical infrastructure. So one server can run multiple applications, and each application runs on its own virtual machine. And these virtual machines are using certain software objects to map back to the host operating system and the physical server in order to function like independent computers. Well, the benefits of virtual machines are better resource pooling, certainly better use of resources. So one physical machine can be divided into multiple virtual machines, allowing the resources to be used more efficiently. Certainly easier to scale. If we need more machines, we just simply go into the hypervisor and create more virtual machines. And VMs in the cloud, so rapid elasticity, meaning that I can stretch my environment. If I need 5 more, I can easily order five more virtual machines. If I need 10 more, I can easily order 10 more. And then I can also scale down as needed. And it is a pay-as-you-go model, typically some kind of a subscription model. So even smaller firms can have access to the resources of the biggest enterprises. And some of the limitations of VM. Each VM still requires capacity allocation, so it still requires access to the hardware. It still requires physical storage. It still requires RAM. The virtual machines share all this, and there is still an entire guest operating system that needs to run on this infrastructure. The more virtual machines you run, the more resources you need, and guest OS could mean wasted resources. And application portability, this is big here. Application portability is not guaranteed. Just because you have a copy of one application and a copy of a virtual machine does not mean if you zip it up and then unzip it and run it that the application is going to run the same. The outer services, the outer physical layers may not allow that. The networking may not allow that. So one response to that, one response to those limitations of the VM was the container. So the idea with the container is the application and the dependencies are all stored in the container. So the container is not a full virtual machine, but it does allow for virtualization of the application and its dependencies. So you can see here Java, the operating system, and a runtime environment such as Tomcat. Here we can see a database, an operating system just as an application such as .NET here. Also we can see here Alpine, which is a tool, and static binary. All in these containers, they all share this common kernel. So these containers represent microservices that are much more portable between the Docker kernels. So here, standardized packaging for the software dependencies. So all of the applications and the dependencies are standardized. Obviously, applications are isolated from one another. They share a common kernel. So they don't share dependencies. And they have, if we look here, we can see an operating system here. We can see things like .NET and Java. So that's not being shared, but the kernel is being shared and works with major Linux and Windows servers. So if we compare containers with VMs, we can see here our container just has the application, and the libraries and the binaries are just here within the containers. Then they run on top of Docker. It's Docker that runs on the host infrastructure and the host OS. So we can see here these containers are quite portable, provided that they are using a compatible Docker environment, and that Docker environment is running on a compatible host OS and infrastructure. So containers are an app level construction, whereas here you see VMs are infrastructure level constructs that turn one machine into many servers. So we can see here there are actually 3 VMs here. They all have their own version of the operating system. They all have their own version of the binaries and libraries, or the dependencies, and they all have their applications running. There's a common hypervisor and a common hardware that the hypervisor is running on. So the containers actually are the microservices. It's very, very limited to just what's needed. Therefore, they're much more robust, much more portable. And the promise of containerization is those containers will run anywhere on any runtime environment, including, in this case, it's Docker. So we can see here containers and VMs together. So we can see here a dev environment, a Docker hosted environment, where we have these 3 applications packaged in the containers with just their dependencies running on the Docker runtime, and Docker is running again on its host OS and infrastructure. Where in the prod environment, Docker is also being hosted with a guest OS. So we can see here the 3 guest OS that are running on top of the hypervisor and the physical hardware. And we can see here that these guest OS have their own Docker runtimes, and these Docker runtimes are supporting apps A and B and their dependencies. App C, which may need the resources of its own Docker runtime and its own guest OS. And then we can see here how this could be a non-containered application that just really needs the application, the dependencies, and its own guest OS. So this is a very, very flexible solution. So some key benefits of Docker containers. So speed, certainly. It's less maintenance because these are all microservices. So no OS to boot, applications online in seconds. Highly, highly portable. Again, Docker containers are not full virtual machines. They're just the application and its dependencies. So provided that the Docker runtime is compatible, the containers can run on top of that Docker runtime. Highly efficient as well. Less operating system overhead and improved VM density, meaning that I can use both containers and VMs together so I can have a more efficient infrastructure with virtual machines and density. I can run more virtual environments because I'm just using containers and not full guest operating systems. So just a little bit of a recap. We had our introduction to Docker and the Docker environment. Our next section is Introduction to Kubernetes. Please follow up with some live classes, including training classes for mastering Docker and containers and cloud deployment, live training classes for mastering Kubernetes, containers, and cloud native, and complete live training for mastering DevOps and all of its tools. Thank you for watching this video on Docker, and this has been a presentation of Coding Bootcamps.